I want to compress some quite important topics that I wanted to cover. So it seems that I will not really be able to say too much about the main part of information theory, I mean the coding theorems. I'll say a little bit, but this will be mainly next week and hopefully touch on it today. But I do want to give you, again, the big picture, which is somehow difficult for those who are really used to see rigorous proofs and all the details. But at the same time, I think I have to choose. I mean, I want all of you to see the big picture first, and then see the details if necessary. So the details simply take time, and you can essentially eventually read them. And I want to really understand the picture. So we briefly, since not all of you were here on Monday, just want to give you again where do we stand. So we defined a model which is called PAC learning. So essentially, it's kind of a simplified version of the general learning problem, which has the following parameters. I just want to remind everybody. I mean, so we have an hypothesis class, which is a class of functions from a sample space to, in general, it can be anything, but we this time think about Boolean function, which is sufficiently general for us right now. And this function is something we want to learn from examples. So we assume that there are examples that are distributed according to some probability distribution, which is denoted by px. And actually, you wrote px and y, but in many cases, you actually think about px and then y equals some target, some function, okay, which may or may not be in the hypothesis class. So it's x and a label y, which may or may not be in the hypothesis class. But essentially, the real randomness here is on how we sample the inputs, x. Okay, so this is what we call the sample space, and we talked about n dimensional or n samples IID in most cases, which are just pair like this, which we call the empirical data. X1, y1 up to xn, yn. So this is the sample. And when we say that S was distributed according to P, we mean that there are IID samples from the probability distribution on X and then labeled by some rule that we want to learn. Okay? And so the requirement of PAC is that given any epsilon greater than 0, of course less than 1 in most cases, and delta greater than 0, both of them actually, of course, less than 1, we can generate, we say that the class is PAC learnable if for any given epsilon and delta, we can find a sample size n of epsilon and delta. There is n of epsilon and delta such that an algorithm, given these n examples, will generate an hypothesis in H, which is not too bad in terms of generalization. So we essentially introduced two important concepts. One of them is what we call the generalization error of an hypothesis H, which was essentially the error that H has on average with respect to P. So this is, in this case, the expectation with respect to P, the true P, the P from which we sample the data, which we usually don't know, we don't want to assume much about it, of the error of H in general. So the error of H is essentially the probability or the disagreement of an hypothesis H with the true label. So this is essentially the measure, which you call by the indicator function, the areas of the points where H is not Y. Is not Y. So H does not produce the right label. And this is what we call the generalization error. Or simply the error, because this is really what we care about. And the other thing is, so this is something which we would like to minimize. And the other thing is what we actually have is the error on the training set. So this is of any hypothesis H, which is essentially can be written in many different ways, but think about it as the expectation over the empirical distribution. Empirical distribution, let's call it PSN, of the same thing, of the indicator that H of X is not Y, which is essentially 1 over the sample size, the sum of the number, the sum of the points, again, I, xi not equal yi. So again, this is 1 if h xi is not yi, and it's 0 if h of xi is yi. That's what I mean by this indicator function. Well, essentially, if you want, this is, again, sum over the errors. This is essentially the intuitive thing, the number of errors in my data, in my sample. Okay? And this is what we call the training error or the empirical error. Training error or empirical error. So these are the things that we want to, that we care about, and the requirement of PAC was that if we are given n epsilon delta, then the probability, okay, so these are the two quantifiers here, and what we want from PAC is that the probability over samples that are generated from P, that the training error minus the generalization error of H, or EP of H, the probability that this is too large, in some sense. So really, this is already, and what we want to say is that given this n of epsilon delta, there is an algorithm that will generate an age, which is not too bad. So the probability that this is larger than epsilon, and actually let me replace this by the best one. Let's call it E star, where E star is the best one in my class. The best one in my class in terms of generalization error. So E star is the best error I can achieve in my class H. Okay? So this will be 0 if what we call the rule is realizable, which means there is an H in big H which actually achieves a 0 error. And this will be something larger than 0 if the rule is what we call unrealizable. Okay, so I just want to unify it now. Yes?
The error itself is not that high.
It's the error itself, that's what I meant. The minimum, yeah, sorry. Absolutely right. The minimum of that. And the best age in some sense is the one that achieves this error. There may be many. Okay, not necessarily unique. So this is the best error. So what I want somehow to unify these two definitions of what we call the agnostic and realizable PAC. It's really very, very similar. We want this error to be small. So the probability that we generate something where the difference between these two is larger than epsilon, we want this to be smaller than delta. So again, and we said, we made this distinction. If this is 0, we call it realizable. Realizable. And if this is greater than 0, which means that there is some error, the best I can achieve is greater than 0, we call it agnostic or unrealizable. Agnostic in the sense that we don't really know where the rule came from, but we want to get the best we can do in this class. Okay? Agnostic or unrealizable. And again, I said at some point, I called it proper, improper. Proper and improper refer to something slightly different, which is related but is different. It's what type of hypothesis I actually generate. So again, this is just to remind you what we're talking about. So you see that in this framework, the whole point is to find an algorithm. Actually, in many cases, we also insist on finding efficient algorithm. What do I mean by efficient algorithm? That its running time is not too large in terms of what? So what are the parameters that we really care about here? Epsilon and delta. So we want, when we say it's efficiently Pak-learnable, so Pak-learnable is if there exists an epsilon delta which will guarantee this, then it's Pak-learnable, okay? But if we also want it to be efficiently Pak-learnable, we want the running time of an algorithm not to be more than polynomial in 1 over epsilon and 1 over delta, which means that if we insist on very good hypothesis, which means good accuracy and good confidence, high confidence, which means small delta, then we're going to pay. We're going to pay in running time as well, not only in samples. So we see, first of all, we are going to get bound on the sample size. So of course, the sample size is usually some sort of lower bound on the running time. I mean, you must run through the samples at least. Okay, actually, this is not always so obvious, but at least this is what we usually assume. So the sample, so what we call n of epsilon and delta is sometimes called the sample complexity. Sample complexity of the algorithm. I mean, how many samples we really need in order to generate a good hypothesis with high confidence. And we don't want this to be too large. I mean, if this is, for example, exponential in 1 over epsilon and 1 over delta, which means that you're going to need huge samples in order to do this. When epsilon and delta get small, this is already not good for us. So the first thing we show that we can actually get good learning in terms of sample complexity. This is also called in some circles information complexity, because it has to do with how much information we really get, how much data we really need. But there's something else which is called the computational complexity. Complexity of the algorithm. Of course, this is very, very familiar to computer scientists. But what we usually mean here is the running time. It can be running time, or also memories. Those are usually somehow you confuse together, but of course the memory is usually, you don't need to access very large memory if you don't need time, but okay, some of them, some sort of combination of these two. Let's think about the running time at this point. We don't care about memory, about space. But in computer science, we actually care very much about not only how long does it take, but how much memory we need in order to run the algorithm. Okay? So these are things which, so far, I didn't say anything about. I mean, what is the computational, complexity of the algorithm? In some cases that we already encountered, the two are very nicely related together. For example, in what we call online learning, and Noga will talk a little bit about it tomorrow, I hope. In online learning, we actually learn by sample. I mean, just like in sequential decisions. I mean, we see another one, and whenever we need more samples. So essentially, the running time and the sample complexity are very slowly connected. I mean, we just need more time and we need more samples. And usually, we have some finite process for each sample, which is not always obvious. I mean, sometimes the question is whether we need to keep all the previous samples or not. It's also a tricky question. You saw already in the context of sufficient statistics, for example, that sometimes we may forget all the previous samples and just update something like the statistic of the data, and so on. So all things are somehow related. Really, the frontier of this area now is in the connections of some interesting questions of what are the real connections between these two things. I mean, can we, for example, trade them? I mean, increase the sample and reduce the computational cost, or vice versa. And in some cases, we know we can. Yeah. So there are many, many interesting examples like this. And the problem can run forever if you have small samples. Like, we can get into all sorts of funny phases that finding the minimum can be incredibly complicated. Spin-glass phases like this, as some of you know. But if you increase the number of samples, suddenly we get out of this complex landscape, and we can do things much simpler, and so on. So there is some interesting interaction between these two things. People are working on it. I'm not going to talk much more about it. So you see that really the key picture that you have to keep in mind is, which I was drawing again and again, are these two functions. The over of the hypothesis class. So H, this is my hypothesis class in some funny one-dimensional way, and these are the errors. So we have EP and the ES, ESN, of the hypothesis. So one is blue and one is red. I'm not sure if I'm consistent with this, but never mind. And so one of them is the average overall hypothesis, and this is some sort of a function which may look like this. This can be 0, or this can be larger than 0. Okay, I don't really care at this point. I mean, it makes a small difference. So maybe if this gap between 0 and the best hypothesis is positive, then we call it unrealizable. If this gap is 0, I mean, there's no gap, I can achieve a 0 error, then it's realizable. Okay, but of course, the training error is a noisy function which fluctuates in general around the true mean. It can, because I can achieve a zero error on a small sample, but not on average, not when I increase the sample. So this is a function of the sample size. Given few samples, I can fit them, get 0 error. So it can be under the minimum. If the minimum is 0, then it of course cannot be under 0. But it can be under the minimum of the blue curve and can be above or below it. I can get a bad sample, which will give me more errors than on average. I can get a good and too good sample, which will give a smaller error than the average. And it can fluctuate, and we know that in general, these two approach each other. So there is a convergence of the red to the blue when n goes to infinity. But essentially, the condition that I wrote just below is the condition that this is never too large. Or actually, this will follow from the fact that this is too large. So there is a property. So this is what we call I call it the fundamental problem of learning, the fact that we actually have the red curve available to us, but we really want to minimize the blue curve. We can't minimize the blue curve because we don't see it. So the question is how well we can do from the red curve. So one simple condition that we already saw, that if the supremum is the maximum, the maximum difference, or the supremum over all h, and h can be infinite, so we have to be careful when we say maximum. It's not necessarily in h. But the best that we can achieve is small. Somehow, if we have a uniform guarantee that these two functions are never too far, this is what we call uniform convergence in this space of functions. And if we can put a uniform bound, so which I can say that with high probability, the red curve is never too far. It's closer, smaller than epsilon, or some function of epsilon, from the blue curve, then we are okay. Why then we're okay? So if we have uniform convergence, if we know that the supremum over h of the difference between EPH and ESH is bounded, let's say, by some epsilon, then why then things like ERM is just one method of doing things. ERM is minimizing the empirical error, minimizing the empirical risk, which is so ERM in this case will find a point on the red curve which has minimum error. So for example, you can find this one or this one or this one or I don't know what. Many points here with minimum error. But if we know that the error is never too far uniformly for all h, so supremum over h means for all h, and h it's never bounded, it's never too far, then we know that ERM, so what ERM will give? So this, for example, is going to be HERM. Okay? This is going to be HERM. and what will be the true minimum here. So it's not necessarily in the same place. The true minimum is this blue one, let's say here. This is going to be H real minimum, the best that we can achieve in this class. Okay? But since we know that the difference is never too large, so we know that the error, the true error of HERM minus the minimum EP of H star, which is precisely what I call E star. Okay? So what is this? So we know that this difference is, how can I bound it if I know that this is true? So I can do the usual trick. This is equal to the difference between EP HERM and this point, first of all. So let's call E. So this is, I want to subtract and add. Yes, this was only with respect to P. This is what I care about. So I write it like this. It's EP of HERM minus ES of HERM. What is this? This is this difference. Okay? Now I added something. I subtract something. I add it again. ES of HERM minus EP of H star. Yes. Okay, so we have essentially three different things here. We know that this is one difference and this is the second difference. This is ES of H star, and this is EP of HERM. Can't read it. And this is it's too noisy. So there are two differences here. This one and this one. Okay? How far is my error from the error at this point? So I'm going to give you HERM, but the error of this HERM is the blue one, the true error. Okay? How far is the error of HERM from the error of H star? This is what I want to bound. Okay, so what can you say about it? So this is first of all due to a triangular inequality. This one is less than this. EP HERM minus ES of HERM. Okay? And plus what? Plus the difference between this and this. Okay? But the difference between this and this, which is this error and this error, is larger than the plus this difference. Okay, so take this one. This I know is going to be smaller than epsilon by my assumption about the uniform convergence, and this I also know is going to be smaller than epsilon by my assumption about EP star. So the difference between these two, and I don't care about this. I care only about the difference in these two. These two cannot be larger than the minimum here. So this is also smaller than epsilon. And sorry, H star. Something is wrong here. Okay, so this, I'm sorry, this is smaller. One of them is, I need to name the fact that this is minimized. So HERM is minimized. So this is certainly larger than, than ES of HERM, of H star. This is smaller than this because it's an ERM. Okay? So, but this is also less than epsilon. So the whole thing is less than 2 epsilon. Okay, so it was a bit convoluted, but it's very simple. I use the fact that this was minimized. This is the minimum, so this is larger than this. Okay? So essentially, uniform convergence guarantee that I have that this, the error of this one, which is the ERM, is not more than 2 epsilon the error of this one. So this intuitive picture that you see here, that if you minimize the red curve, and the red curve is always close enough to the blue curve, then you can't be too bad. This is precisely what it means. Simply the triangular inequality plus the assumption that I minimize the empirical error. Okay, so this is why this condition is going to be our fundamental requirement. There's a little jump here. So this idea of uniform convergence, I mean that everywhere this is closed, is something we really want to bound in general. Okay. So this is something I missed last time, and I wanted to verify that you understand it. Is this clear? Any question about it? The only tricky thing here is that this is simply is the fact that this one is larger than this one. Okay, and therefore I can bound it like this. Okay, so we essentially got several types of bounds, which are really important. So these are all what we call sample complexity bounds. So again, at this point, we completely ignore the issue of computational complexity. So these sample complexity bounds are interesting because they're usually easier to obtain and much more general. So essentially, we got 2 types of bounds. One of them for the realizable case, which is essentially what we call the cardinality bound, which was that n should be larger than 1 over epsilon log the cardinality of H over delta. This is typically what we get. I mean, I hope you remember how we got it. It was relatively simple to prove. All we essentially bounded here using the union bound is the probability that a sample of size n will miss an epsilon bad hypothesis, and then we bounded it that there exists, that such hypothesis actually exists by multiplying by the cardinality of H. And this is how the cardinality of H got here. So this is what we call cardinality, realizable cardinality bound. In some sense, this is the, once you understand this, you really got the basic idea. Then we had another one for the unrealizable case, which was essentially what? Essentially what we got there is that we have a bound on the distance between epsilon p of H minus epsilon s of H. And we saw that this is larger than, so the probability that this is larger than something which came out of the Hofstadter inequality. So we use the fact that the empirical error is a sum of independent random variables. And since it's a sum of independent bounded, in this case plus minus 1, random variables, we know that in the limit are going to converge to a Gaussian distribution. And essentially asking, this is going to be the mean of this Gaussian distribution, this is going to be the empirical value, and asking how far you are from the mean of a Gaussian distribution is something we can bound for Gaussians, okay? It's the integral of the error functions. Okay, the tails of the Gaussians. And we know how to bound the tails of the error function. Essentially, this is something I missed last time. So if you have a Gaussian, and it's supposed to be a Gaussian, and this is the mean, and you're asking yourself, what is the probability that you are further than some epsilon from the mean? So it's the areas of these things. And this is what we call the two-sided deviation. We can also, actually, we care only about the one-side deviation because we really don't care if our true error is, generalization error is smaller. We only care that the generalization error is not larger than something. So we really care about only one-side deviation. But even these two-side deviations, what is the probability in the Gaussian that you fall in this tails of the distribution. This is bounded by this is known as the complementary error function. You may have heard about it. It's the integral of the Gaussian from this point to infinity twice. Okay. With this, you can verify yourself that this is bounded actually by the value of the Gaussian itself, more or less, up to some constant. So this gives us this nice bound, 1 over 2 to the n log. Here I'm actually using the two-sided bound over delta. And I'm sorry. Yes. So the probability that this is larger than this is smaller than delta. This is what we want eventually. Okay? So notice that if we want this to be epsilon, to be smaller than epsilon, then we get immediately a connection between epsilon and delta and the cardinality of H. So this came from the Hofding bound. Hofding inequality, which is some sort of a normal approximation of the sum. So if you don't remember where it came from, just remember that you want to bound the tails of the Gaussian distribution, and you need the bound on the error function. I hope this is enough for this one. Okay, so this was the unrealizable case. So essentially, if you look at the nature of these two bounds, both of them have essentially the same nature. It's a connection between n, epsilon, and delta, and the cardinality of H. So this will give us a slightly worse bound. And the reason we have the square root here is because the bound on the tails of the Gaussian look like e to the minus x squared, if this is the integral of the Gaussian. Again, the integral of the Gaussian from x to infinity is bounded by this number. Okay, and x was in this case epsilon n, epsilon square n. The epsilon square come from the x square, and n come from the variance. So the variance is 1 over n, and this is essentially what we see. So it's really very intuitive once you understand this. So I usually don't remember anything by heart. Just remember where it came from, and then if you need in the exam, convince me that you understand where it came from. It's enough. It's much better than actually be accurate about the constants. Believe me. Okay, so this is the unrealizable case. This is giving us a 1 over n type of decay of the error, and this is giving us 1 over square root of n type of decay of the error. Okay, so now we started to ask, can we improve it to infinite H? Infinite H. What happened then? And we introduced that. I did it on Monday, so not all of you were there. We introduced two types of way of thinking about infinite H. So essentially, if you look at this bound, you see that what we really care about is that this type of quantities, or this type of quantities, which involve n and h, and maybe epsilon as well, are such that we can actually bound them. So essentially, this we want to eventually. So all those bounds have the following form, and this is something slightly more general. So let's take a zoom out a little bit and see what is the nature of the thing that we get here. So the nature is all coming from essentially the union bound or some variation of the union bound, that the cardinality of H times some function that goes like e to the minus n times some other function of epsilon. So this function of epsilon was epsilon, so it's actually greater than 0 and monotonically increasing, was epsilon in this case, and was epsilon squared in this case, and so on. It's usually a growing function of epsilon. So this was a realizable case, this was unrealized. So this is some function of epsilon. And what we want is that we should be able to find n such that this is sufficiently small. If we can do this, then we are fine. Now, if you look at, now we want to, obviously, if this is infinite, then this is hard to do. Okay. So we need, if this was finite, we can find n. If f of epsilon is not crazy, it's like epsilon squared, or some polynomial of epsilon, then we are fine. I mean, we just need to do, but notice that this has, by the way, this can write it as e to the log h plus, or minus, sorry, n minus epsilon, nf epsilon. And what we want is that eventually, for large enough n, this will be as small as we want, smaller than delta. Okay? So for this, what we really need is that for large enough n, this exponent is less than 0. Okay? So what is log of the cardinality of H? So log of the cardinality of H, what it reminds you of something? I mean, log of the cardinality of space in general, or possible hypotheses, or possible options, or possible configurations. What is it? It's called entropy in physics. I mean, essentially, maybe you don't see it now, but this is remember the entropy that we defined already was the worst possible case for finite spaces was simply the log of the dimension, the log of the number of possibilities. So this is some sort of entropy. Let's call it entropy. Quotation, it's some sort of entropy. And this is some sort of error. So this is something you want to minimize. I mean, we want to minimize epsilon. So this is competing with the entropy. So the entropy is going to explode on us. It's a complexity measure. This is some sort of complexity term. Complexity term. The larger it is, the more complex H is, in some sense. And this is some sort of bound that comes either from Hofding or from some other probability type of bound, what we call usually measure concentration bound, that forces this to be, we want this to be small, but the complexity term is hurting us. So we really have something which looks like a competition between entropy and something that physicists would like to call energy. Why energy? Because this is something we want to be small. And something, this is what we want to compete with this. So this is generally true in all those kinds of problems that they essentially reduce to a competition between two terms, a complexity term and an error term. This error term we want to minimize, so in some sort of energy. So all the physicists here, I'm not sure, or at least this should remind them of the basic structure of statistical physics. I mean, we have here a competition between complexity and energy, and as long as the complexity is not too big, then the energy term eventually wins. Okay? So this is the idea of how to extend it to infinite classes. We somehow want to bound the complexity, but the complexity can still increase. It can increase both with n or with epsilon. But as long as it doesn't increase too much, in terms that this is eventually going to find large enough s when this linear term in n is going to win over this, then I'm going to be fine. So I want to extend now the hypothesis class to be much larger, either as a function of epsilon or as a function of n. As long as I can do this, this bound will eventually be small enough to win, to allow me to learn, which means I can put it as small as I want, less than delta. So as long as this is positive, I'm not good. If this is negative and multiplied by some large number n, I'm okay. So this opens actually the way to many, many possible ways of bounding it. And since we don't have time here to really talk about everything, so I gave you two interesting ideas. One of them are actually, I wanted to mention another one. The first one is what we call the Occam principle, Occam razor. So Occam razor was based on the assumption that I can bound the cardinality of H by some function of n, sample size. So for example, I know that my algorithm generates hypotheses which are not too large. Okay, so Occam razor was the output H has a size in bits which is smaller than some constant n to some power, where there's some power. Beta is actually a bad choice for this. This power is less than 1. Maybe 0 if I don't care about 0. So which means that the hypothesis that the algorithm generates, I don't know, it may be an infinite class, but eventually I get a list of bits which describes my algorithm. And this list of bits should not grow too fast with the sample size. If it's growing slower than the sample size, then I claim that we can generalize. Why can we generalize? Because then again, so in this case, what I can, the effective size of age is now going to be age is actually a sample which depends, a function, a space which depends on my sample size. So the more samples I'm given, I have maybe more complex hypothesis. But as long as this effective size of age, so I know it's bounded by the way, this size of age should be true for any rule underneath. So this is a uniform bound for all age given n. Okay, for all age. This is what I'm going to get. So this is bounded by 2 to the a n to the beta. Why is this true? Because I can describe all the hypotheses there by exactly this number of bits. So I can index them by this number of bits. So no more than this number of hypotheses can be there. So this is the finite space again. And since this is a finite space again, I can plug this here. And what I get is that essentially 2 to the a n beta times, let's call it e. Okay, just to make life a little easier. Yeah, it doesn't matter. So it's ln e multiplied by ln 2. Okay, I don't care about this. Sorry. So this is in nuts. Natural units of. Okay, if you are confused, just put the ln 2 here. It's a constant. Don't care about constants like this at this point of the course. So e to the n beta minus n f of epsilon. When will this be sufficiently small for large n? So as long as beta is less than 1, this behaves like e to the n to the power 1 minus beta. Sorry, this behaves like n. So this thing, well, actually, the easiest way to say it is that this grows slower than this, because beta is less than 1. And since this grows slower than this, at some point, the whole thing will be smaller than 0. The whole thing will be smaller than 0, then I can make it as small as I want eventually. Okay. So if n if beta is less than 1, the complexity term is going to grow slower than the energy term, and eventually the energy term will mean. Okay, so you see that I could eventually make this for n large enough, smaller than that. And this essentially for edge large enough. Large enough, I don't care. It doesn't have to be infinity. Large enough, this will be negative. Okay, so this is the idea of the Occam. So if I can compress, I can generalize. This is what, and notice, by the way, that I don't care if this f of epsilon was epsilon, or epsilon squared, or epsilon to the 17th. As long as the dependence on n is such, I'm okay. This is one idea. It's actually a very interesting idea. So anything that compresses the data, this generate hypothesis is actually give me less bits than the sample size, generalize, or Puck learnable. Okay, the other idea was to take as, this is what we call epsilon nets. Epsilon nets, or covers. Epsilon cover. It's also a very fundamental and very useful tool. If I could somehow cover my hypothesis class with a finite set of hypotheses, which are nowhere further than epsilon from any other hypothesis. Okay, think about it like a grid. You know, you have the plane. Let's say you have a compact part of the plane. Actually, it doesn't have to be compact. If I have a distribution which somehow decays to the tails, I really don't care about the tails too much. I can compactify it with high probability. So anything which has a distribution on it is essentially compact almost automatically by the distribution. But if it's just a compact like the unit square, so the unit square, for example, 0, 1, 0, 1 is of course an infinite space, but I can find, with respect to the uniform distribution, I can find a grid here. Okay? I can find a grid And if I make this an epsilon grid, then it's a finite set. It has essentially 1 over epsilon square points. Okay? And the point on this grid, the point that every point in H in the space here is not further away than square, in this case, square root of 2 of epsilon or something like this, epsilon from the point on the grid. So I can replace my infinite H by a finite grid on H. This is what we call a finite epsilon net. Okay, so the condition now is going to be, I'm going to replace H by what I call H of epsilon, which is a finite net or grid. And of course, the condition is, the assumption is that I can do this with not hurting myself by something like epsilon over 2 or some simple function of epsilon. So if I learn this and give you 1 point on the grid instead of the true H, I'm not going to be too bad. I'm going to be at most epsilon over something from what I want. Okay, so essentially, it's a very simple idea. In terms of this fundamental picture, what I do here, where is this? In terms of this picture, what I do essentially is discretize the space here, make it finite. As long as I know that every point in H is not too far away from any point on my grid, I can work with the grid instead of with the true H. Okay? It's a very simple idea. Very powerful. I mean, we can do a lot with it. So, and what we saw is that, in a sense, if I can cover H with an epsilon grid, which doesn't grow too fast with epsilon, so if this H of epsilon is bounded, let's say, by some constant, by some O of 1 over epsilon to the D, to some constant D, this is exactly what happens in the topological geometrical dimension. If there is some finite D, which I eventually want to call the dimension of H, the topological dimension of the H, then I'm fine. Why am I fine again? Because, again, plugging this here, log of this is going to look like D log over epsilon. So I'm replacing, so this is the assumption of a finite dimensional H. So it has an epsilon cover. And with respect to what metric, by the way? I mean, what is my measure of distance between hypotheses? It's not a DKL, no. It's not yet a DKL. It's going to be the DKL at some point, but what is the natural distance measure here? Just want to make sure that you're not really with me. Okay, so it's not good. What measures the distance between hypotheses in this problem? When do I say that an hypothesis H is close to an hypothesis, has a distance epsilon from H prime? Generalization error, of course. So what I want is they are close in the measure of error. Yeah? How well they agree on the data. So the metric with respect to which, so this is also called the finite metric dimension. Okay, so I'm covering my space with spheres of size epsilon. In this particular measure of error, measure of distance, the probability that they disagree on a new example. Okay, so there's only slight problem with this is that I don't have this. My assumption is that I don't know the distribution, and therefore I cannot measure this distance. So but otherwise, if my space has a finite dimension, and I can cover it with an epsilon net, in principle I'm okay. Why am I okay? Because then I plug this finite. This is a finite set now. I plug this finite set in the finite bound. And what I get here, again, so in terms of this entropy energy competition, the entropy now is going to be the log of H epsilon. Okay, let me write it here. So I replace H by H epsilon. That's what I said here. And I'm going to get that e to the log of H epsilon minus this n function of epsilon. This is what I want to be eventually smaller than 0, or the whole thing I want to be smaller than 1. This is going to be more or less e to the log of H of epsilon going to be d log of 1 over epsilon. Because I assume that the size of H epsilon is proportional to 1 over epsilon to the d. This is my covering assumption. Okay? So I'm going to get d log of minus epsilon minus n f of epsilon. And this is going to, and the whole thing should be less than delta. So this is going to give me a bound of the form n greater than, if I compare it to this one, it's going to be like d over epsilon, but instead of log h here, I remain with d log 1 over epsilon. So it's going to give me here log of 1 over epsilon plus log of 1 over delta. I actually put a factor of d on the log of 1 over delta. I don't care about it. So this is a small worsening of the bound. I don't really need the d over the 1 over the delta, but this is the type of bound I get from epsilon covers. In this case, and if I put it in this case, I'll get the square root outside if I want to bound n. Well, otherwise, it's going to be very, very similar. Okay. So this is the epsilon net. Any questions about it? So you discretize your space, and then you have, okay, you can use the cardinality bound again. Notice here that the assumption is that if you want better epsilon, what you need to do first is find a nice grid. Okay? Once you found a nice grid, learn with the finite learning algorithm, the finite cardinality learning algorithm, and then you know that you generated an approximation which is not too far from what you wanted, not more than some function of epsilon. Of course, now I have to play exactly with the epsilon such that everything will match. So it's maybe epsilon over 2, or 2 over epsilon, who cares? I mean, these are called constants. I mean, okay, you have seen epsilontics in NP. I hope not long. How exactly I play with the epsilon is easy as long as I'm fine here. So now the point is, there's one big problem, as I mentioned. In order to create this cover, this epsilon net, I really need to know the probability. I don't have the probability. So what do you suggest? What could be a good replacement? The empirical probability, right? It's very simple. So essentially, in order to show that this procedure, this idea actually works, I need to show that if I replace my error measure, my distance measure, instead of having the true probability of error, the empirical probability of error, I'm not too bad. Empirical probability of error I do have. In principle, the algorithm has the empirical probability of error of any hypothesis in my class. Okay, so why am I not too bad? Again, I'm not too bad if I know that these curves are closed. So if I have some supremum, some bound on the supremum distance here, some uniform convergence, then I know I'm not too bad if I replace the probability by the empirical one, as long as I have guaranteed that I'm not too far away, because essentially I can bound the difference between the true error, or the true distance, and the empirical distance by something which depends only on epsilon. So here I have to do some work. Not very much work. You could read it in many, many books. How to replace the epsilon net from the true epsilon net to the empirical epsilon net. And this is essentially how these algorithms work. I mean, so I generate an epsilon net using the empirical error, and using the uniform convergence assumption, I guarantee that it's not too far away from a grid over with the true one. So in my picture here, what you do is replace this grid by a noisy grid which is based on the empirical error. But since I know that my empirical error is going to converge to the true error, for large enough n, these grids are going to be similar, close enough. So I make it a finite grid, because I want to make finite grid with empirical error such that it well approximated the true error. So this is the end of this chapter. So the question now, I'm actually skipping the break. No, I don't want to skip the break. So let's stop here. But of course, now I want to show you some concrete bound like this. What is this D again? So do I really need to estimate the dimension of my space? This can be a big headache to think about it, space of functions. So I want to replace this with something much more accessible, which in many cases is introduced directly, but since this is a somewhat complicated concept, so I want to show that this D here can be replaced by something which we call the VC dimension, DVC. So in some sense, I really don't need to worry about covering my space with a grid, with an epsilon net, but somehow I can look for a simpler combinatorial property of my hypothesis class, which will effectively act like a dimension. So this is going to be the topic of the next hour. It's called the VC dimension. I'm going to squeeze it into 1 hour. I hope I can. And then so essentially I just want we're going to make some sort of a nice function, combinatorial function of this class, which essentially measures the complexity and eventually allow me to cover my space with epsilon net, but I'm not going to use epsilon net directly. There's a problem with the VC dimension. It's the way it is defined. It's defined only for Boolean functions. And if I really want to extend it to non-Boolean functions, one way or another, I need to go back to the notion of epsilon nets, or an epsilon approximation. Those of you who know something about mathematical, the theory of approximations in general, I don't know how many of you learned something about it. So you know the approximation essentially, let's say I want to approximate a function with a function in a class. For example, I want to approximate a function by a sum of sines and cosines. This is called Fourier approximation, for example. So this I can do as long as I know in what metric I approximate my space. So I can approximate, let's say, with Fourier series or Fourier series, any function in some binary class, and the measure of distance there is usually taken as the L-square measure. I mean, the difference, the integral of the square difference of the functions. So in this case, and again, the idea of approximation theory is to build an epsilon net. If I don't tell you. If you want a regression, let's say a regression function, you want to approximate data with a polynomial, we actually used already the L-square measure. So this is, again, we have a measure of distance, and in order to approximate it with a nice function space, we need an epsilon net. So the idea of epsilon net comes again and again whenever you talk about approximating things. There's nothing special about learning theory in this case. So learning theory is just a theory of generating an approximate hypothesis. The only problem with learning theory is that we don't have the metric. We have only an empirical metric, and we need to do the same thing only from finite data. So that's introducing some sort of complex questions, which are all essentially settled by this assumption of uniform convergence, that I can approximate my true one with the empirical one. Okay, was this too high level? I don't know. Okay, you need the details, but at least now the picture should be in some way clear. Let's take 10 minutes again. מטריקה זה ההסתברות של הסיכונים.
ההפרש של ה-IP?
כן. סליחה, זה ה-probability של h1x is not equal to h2x.
אבל רגע, אבל פה יש לך עבור כל a.
זה מה שכתבתי, measure של h... זה שטח... זאת מטריקה. סימטרי, חיובי, אבל האמת היא שזה לא חשוב. מה שחשוב שאני יכול לקרוא, גם אם זה לא היה סימטרי, מה שחשוב שאני יכול לכל נקודה למצוא קירוב אצלון במרחב שלי. ממש לא מעניין אותי אצלון שלה. אבל אם זה מטריקה, אז יש לנו גם מטריקים טופולוגיים יפים, כיסוי של משפטים זה באמת עוזר. ואז הממד הבלתי הוא בדיוק הממד הטופולוגי של המרחב.
יש איזה משפט
מלא משפטים, בעניין הזה של הטופולוגיה, זה דברים די פשוטים, אבל יש להם המון טוב מתמטיות ששונות. בגדול, כל מרחב טופולוגי בממד B, קטע, מישור, מרחב, אני יכול לעשות אותו, זה אחד קטע של Z. כל מטר. אם הוא קומפקט,
תלוי במידת ההסתברות על x. גם אם x היא לא קומפקטית של כל הישר, נניח שיש לזה איזושהי התפלגות. נניח שיש לזה התפלגות, אז זה אומר שאני יכול למצוא קבוצה קומפקטית, תתפוס אחד מינוס דלתא מהמעלה.
אבל אתה לא תצליח להגיע למשהו פורום. אם המטריקה שלך היא הסתברותית, לא?
שאלה טובה. קודם כל, מה חושב משהו יותר פשוט? קודם כל נתן לזה קומפוסיטיקה. אני יכול לחתוך מתוך הישר המשיק קטע בסתברות שלה היא גדולה מאחד מה? בכל דלתא, בסתברות שלה היא גדולה מאחד מינוס דלתא. זה יהיה קטע קומפקט, אז הייתי חסך קטע זמנות. לא יכול להיות שיש קטע אינסופי שהמזר שלו הוא גדול מדי. אז ברגע שחסכתי את הדלתא מזר, ואז אני בעצם עושה את המרחב הקומפקטי שנוצר על ידי שחסכתי דלתא. אני אקח איזושהי התפלגות, בגלל שהתפלגות היא ניתנת במרחב, אז זה אומר שאני יכול לשרוק אזורים של מרחב שבהם המזר קטן מדי. לא מעניין אותי, מידת דלתא לא מעניינת, זה לא מה שכל השקל לא רואים, כל מה שקל משפור שנה מדלתא לא מעניינת. אז אני אעשה את זה ככה. דבר שני שאני יכול לעשות זה באמת למפות את ההתפלגות שלי בהתפלגות אחידה על הקטע הזה. זה אתה יכול לעשות למשל עם measures בארבע ממשיים, זה היה תנקיר. וכל מיני דברים, יש לך את ה-CDF ההפוך, נכון? זאת האינטגרל של הצפיפות. נניח במקרה גאוסי זה האופן. אז הפונקציה הזאת היא פונקציה חד ערכית בדרך כלל, שממפה כל נקודה ב-x לקטע x. נכון, זה פונקציה הפוכה. אז על ידי המיפוי הזה אני עושה קומפוסיטיקציה של מרחב ואני מעביר אותה הנה. ולא שאני מעביר אותה הנה, אלא ההתפלגות על קטע f1 היא יחידה. עכשיו תבנה אפסילון קאבר של קטע f1. אני דווקא לדייק באיזשהו משהו. ותמפה אותו דרך ה-CDF שלך, תיתן לך כיסוי אפסילון סופי. באופן תאורטי, אני יכול לעשות את זה גם במדעים כאלה. המיפוי האופי הזה דרך ה-CDF, מה שאתה רואה כאן, אנחנו מתחילים להתבדרות. רק בגאוסים, גם במדעים, אני יכול לעשות את זה בצורה יעילה. ממד. זה מדהים. רק רואים לך שברגע שאתה מדבר על מידת הסתברות על המפה שלך, באיזשהו מובן אתה עושה אותה קומפקטית. כל מה שאתה צריך להגיד, בוא נחתוך הסתברות דלתא, ואז אני חושב, זה לא דבר כאן. שכחתי את כל הקטע לאיזה כדור אחד קטן פה. כל דבר כמעט, אם חסר עכשיו את זה בכדורי אפסילון, אז כמעט כל הישר ייפול לכדור ראשון ואחרון. מה שזה מטריד. המידה של השתיים האלה היא קטנה מספיק. שהנקודה לא חשבה. זה כל הרעיון. כן. שעה?
פה יש לך... זה הישר אינסופי. למה? למה? אתה אמרת בזה שאתה רוצה שתקבל שאתה אינסופי.
לא, אני אומר, זה אינסופי, התכוונתי שאינסופי במרחב. גם הקטע 0-1 זה אינסופי. יש שני דברים. יש מה שנקרא קומפקטי, יש אינסופי. קומפקטי זה אומר שהוא כמו הישר 0-1. יש בו אינסוף נקודות, יש אפילו רצף של נקודות. אבל הוא עדיין נמצא לכיסוי סופי.
כאילו היה סופי.
זה היה אינסופי, אז זה לא משנה לי. זה מה שאמרתי לו עכשיו, בדיוק מה שאמרתי לו עכשיו. גם את הישר האינסופי אני יכול למפות לתוך הקטע 0-1 על ידי שאני מפות אותו דרך ההסתברות ההופכית. כשאני דרך ההסתברות ההופכית אני יכול עכשיו לייצר קאבר סופי של דבר פארה הזה ולפתוח אותו חזרה לישר המלא דרך ההסתברות ההופכית.
אז היה כאילו קטע סופי
אבל אנחנו חייבים לדבר דברים קומפקטיים, בסדר? זאת אומרת, תחשוב שההיפותזות שלי עכשיו יש להם אינדקס ממשי. זה מרחב ועוצמת הרצף. אבל הקטע 0-1, כמו שהמיפוי הזה מראה, הוא שקול מבחינת עצמה לישר הממשי כולו. יש לי הנה מיפוי חד חד-ערכי ביניהם. אתה מפעיל אותם דרך האירופן. זה דרך הסיגמואיד, זה דרך עוד פונקציה כזה של חד חד-ערכי בין 0-1. יש לי כאן בעיה לכאורה עם הקומפקטיפיקציה, כי אני הנחתי שיש כיסוי סופי למרחב שלי. אני אומר, אם אין קישור סופי, זה נקרא קומפקטית. קבוצה קומפקטית זה בדיוק קבוצה שניתן לעשות אותה לכל X על ידי מספר סופי של כדורים. לכל X. עכשיו, אתה אומר, ישר המשי הוא לא כזה, נכון? אבל כיוון שיש לי מידת הסתברות על המרחק שלי, אז אני יכול לחתוך ממנו דלתא הסתברות, ואז אני נהיה קומפקטי. בסוף פשוט כל הדברים שמפריעים לך, זה לא יכול להיות שיש לך מרחק לא קומפקטי, שההסתברות היא לא חסומה שם, כי זה אומר שהמידת הסתברות שלנו היא לא מנורמלת. זה לא יכול להיות. אז בגלל שהיא מנורמלת, תוך כדי זה בדיוק מה שעושה לי את דלתא. עכשיו לי לחתוך את הזנבות שלא מנהל. שאלות קשות, אבל אני רוצה שתבינו לפחות האינטואיציה.
לא, עכשיו הבנתי.
זה שאלה לגבי היוניפורם. זה משהו שמניחים, מוכיחים, כלומר עבור כל מחלקה אני צריך להוכיח שקיימת איזה יוניפורם.
נכון.
אנחנו הוכחנו את זה בכל ספרייה, כלומר מה
יפה, שאלה טובה. בדיוק שפעת לך עוד. נתן לך איזה משפט קונסטרוקטיבי שאומר בקלאס הזה יש יוניפורם כזה.
אוקיי, אז צריך להוכיח שזה גם בקלאס ואז אפשר להשתמש.
ודאי צריך להוכיח. התכונה שלי מרחב ההיפותזות. אני אמרתי, אם מרחב ההיפותזות...
אנחנו מניחים את זה עכשיו ועכשיו...
אני אמרתי, אם הוא סופי, אין בעיה. סופי, כל המרחבים הסופיים הוכחנו שהם יש להם יוניפורם כזה. אבל זה טריוויאלי, משום ששוב אתה מחסום את הרע ביותר. אז זה מספר סופי של דברים, מחסום את הרע ביותר שהם יש להם יוניפורם כזה.
אבל אם הוא
מרחבים אינסופיים.
השאלה, הוא עדיין יכול לקיים.
לפני שעברתי מרחבים אינסופיים, אמרתי בוא נקרב את המרחבים האינסופיים למרחבים סופיים. עשיתי כאן שני סוגים של קירובים. אחד זה על ידי N, זאת אומרת, זה לא גדל יותר מדי מהר עם N, ואז אמרתי, זה איפה נקיים מרחב סופי כמובן, כי N ביטים זה N ביטים.
אבל זה לא תמיד יעבוד, נכון?
אם אני מוצא אלגוריתם שמייצר היפותזות שהתיאור שלהם תמיד סופי, אם גדול מאוד. אם האלגוריתם שלנו הוא סוג של אופן אחר, הוא גם מייצר נט. אלטרנטיבה אחרת, אז זה נתן לי מיד מרחב סופי, והכל היה בסדר. עד המרחב הסופי הזה, הוכחנו לך התפצלות של אינפורם במרחב הסופי בעזרת חסם קרדינלי.
אבל באמת,
הדרך השנייה הייתה לפצות את המרחב. זה הנחה שנראית יותר קשה, אבל ברור שלא תמיד כאלה. לא תמיד אתה יכול למצוא ממד סופי או משהו כזה שאפסילון נט גדל עם שתייה. יכול להיות, דרך אגב, שאני יכול לעשות את זה, אבל הדימנשן הזה יהיה תלוי באפסילון. עכשיו, קצת דומה בלמידה, כי אני עשיתי את הקלאסטרים. קלאסטרים, שאלו אותי גם הרבה אנשים, ושאלה מאוד מוצדקת ונכונה, איך אתה יודע מה מספר הקלאסטר? אז באמת, אתה לא יודע, באופן עקרוני, כך לכל נקודה תהיה קלאסטר. אם אתה משל לכל נקודה קלאסטר, שגיאה היא אפס, נדע, אולם זה לא טוב, מצבים של הגדלה, משום שזה אומר שההיפותזה שלך, כשתאר את ההיפותזה, כדי לתאר את הקלאסטרים, אתה צריך לזהר את הנקודות. כלומר, לכל נקודת שם קלאסטר, יפה מאוד, זה אומר שלא דחת את הנקודות. כלומר, שההיפותזה שלך, התיאור שלהם ילך כמו N. בכל נקודה אני צריך לשים פרמטר, פחות ביט אחד. אבל אם תשים פחות קלאסטרים מ-N, כלומר, אם מספר קלאסטרים יגדל יותר לאט, יכול לגדול עם N, אבל יגדל יותר לאט מהם, שהשורש שלו. או לוגן, או משהו כזה, אז אני יודע שזה בסדר. באיזשהו מובן, משפט האחרונה זה מבטיח לי, מה זאת אומרת מבטיח לי? מבטיח לי שאני תיקח עכשיו עוד מדגם. אז תיקח מדגם אחר, בלתי תלוי, ותעשה לה קלאסטרים, שני הקלאסטרים האלה לא דומים. זה בדיוק הרעיון של הפרדה בקלאסטרים. תיקח שני מדגמים, אני מגח מדגם אחד של האוכלוסייה, ואני רוצה לחלוט את הסביבות, אז וגם עוד מדגם, הייתי רוצה לקבל אותה התפלגות, נכון, בסטטוס טוב. זאת אומרת שאני רוצה שהקלאסטרים שמדגם למדגם יהיו חסומים. זה בדיוק מה שהיוניפורם קונברג'נס בא זה מצליחים. כשאני אומר שמרחק ההכללה, שגיאת ההכללה לא רחוקה מהסגיאה האמפירית, הוא אומר ששתי שגיאות אמפיריות תהיינה קרובות.
שתי שגיאות אמפיריות? אולי האמיתית שלהם שונה.
לא, שתיהן תהיינה קרובות האמיתית.
שלהם, אבל כל אחד מהם...
אני לא יכול להיות יותר רחוקות אחד לשנייה. נכון? מקסימום שני אפסילון. אני לא בטוח שכל שנייה לקרוא את זה. זה יהיה אפסילון וזה יהיה עוד אפסילון, המרחק של שניהם, משני מדגמים לא יותר משני אפסילון. שני אפסילון. אז כמה אפסילון אחרי כל אפסילון. עכשיו, אז הרעיון הוא שאם יש לי יוניפורם קונברג'נס, אני יודע שכל השגיאות האמפיריות לא רחוקות מדי אחת מהשנייה. זה אומר שהשגיאה, מה שעשה עצמך מדגם אחד, לא יהיה מאוד רחוק מה שעשה עצמך מדגם אחד. זה המטרה של הרעיון.
אבל אם אני משתמש ERN, רק אם אני...
לא, אני אפילו לא אמרתי, ERN השתמשתי בו, ברגע שיש לנו
ERN לא יכולת להגיע.
בכל מקום זה יהיה קרוב, אוקיי? בפרט זה יהיה קרוב פה. ברגע שהשני הקווים האלה...
בין השגיאה שלו לבין השגיאה שלו.
לא, בוודאי שלא, אבל גם בנקודה הזאת, אני יודע שהמרחק הוא לא יותר מדי רחוק.
אבל מהאמיתי, לא מהשגיאה...
מהשגיאה שלו.
כן, אבל לא מהשגיאת מדגם אחר.
נכון, אתה אומר שאתה נזהר עכשיו את הקו האדום, אבל אני לא רוצה לעשות ERN. אני רוצה לעשות משהו אחר. ERN זה יכול להיות קשה מזה. יכול להיות שאתה עושה סימולייד אנילי, אתה עושה פה רעש, אתה עושה איזשהו גרדיאנט דיסנט, שיגע אותך למשהו שאתה רוצה להבטיח שלא תיתקע במימון מאוד רע. יכול תיתקע פה או תיתקע פה. איך אתה יודע, קצת פה, איך אתה יודע שזה כמה זה רחוק מזה. אתה לא יודע באמת. לכן כל השגיאות, כל האלגוריתמים האמפיריים האלה כמו הסוג של סיגנל דיסנט, רפליגיישן, יכולים לתקוע אותך בכל מקומות לא טובים. אבל אתה יודע שמה שמצאת בתוחלת של השגיאה שלו לא יותר לרחוק מהתוחלת האמיתית שלו. אז אם זה מספיק טוב לך, מי אמר שאני צריך למצוא יותר מגמי? החיים, כשאתה אומר ביולוגיה, כמו שאומרים בכל הזמן, אני אף פעם לא יכול להבטיח שהמערכת מצאה את האופטימום גלובלי. ואיפה שצריכה למצוא משהו מספיק טוב. זאת אומרת, יותר טוב מהמחקר שלך. אז זה בדיוק מה שקורה, כי אנחנו מוצאים משהו, יכול להיות שזה מספיק טוב לי, כי המחקר שלי לא הגיע לתואר שיותר טוב. אז הרבה פעמים מעניין אותי דווקא התכנסות, לא דווקא במינימום, אלא בכל מקום. נכון, שאתה רואה לי כאן שהגישה הזאת של ביולוגיה קונברגנט היא מאוד חזקה. כן, אולי חזקה מדי. אולי חזקה מדי. באמת אפשר להראות שבעבודות האלה שבשנה האחרונה, השנים האחרונות שאנשים יפקו על זה, כמו לי דניאלי ושי שואל, עבדו קצת העניין הזה, שאפשר לרוקח, אני יכול להניח שזה לא, שזה רק קרוב במינימום או באזור מינימום, במקומות אחרים זה מתרחק, אבל זה ברור שזה לא לזה. איפה בדיוק נמצאת ההיפותזה הנכונה שלי אני לא יודע, אבל אני צריך להבטיח איזה משהו שזה לא מתרחק יותר מדי מהר. אפשר קצת לרכך את העניין הזה של המינימום קונברגנט, המינימום קונברגנט שזה תנאי מאוד יציב, שהרבה שנים חשבו שהוא חסר מספיק למידה. ואנחנו יודעים שהוא לא הכרחי. תודה רבה. אני לא שם לב למה טוב, תקראו בבקשה לחברים שלכם. So I got, as usual, many good questions during the break, and this is actually very encouraging because some of you really follow me. One question is repeated several times. I want to share it with you. So first of all, when I said infinite H, there are two notions that you have to be careful about. One of them is what we call compact. So for example, the 0, 1 interval is infinite in terms of number of points. Okay? How many points are there? Aleph. Okay. We all know what Aleph is? Of course you know, but this Aleph. So Aleph is the measure of the continuum, and I'm not going to say much more about it because I love to say it, but it's not. It's out of the scope of this lecture. So it's more than, for example, how many rationals are there? It's also infinite. it's actually a dense set. It's for all practical purposes, it's the same, but it's still a very different size. Okay. So, but it can be also uncompact in the sense that, for example, it can be the whole line. So the whole line, even if I just talk about the integers, I mean, it's a non-compact space in the sense that I cannot cover it with a finite number of spheres of any epsilon. Okay? So in principle, this H can be indexed by the numbers between 0 and 1. This means that, okay, it's a power Aleph, like all the intervals, all the semi-intervals, these are all in terms of cardinality. How many rectangles are in the unit sphere? It's all Aleph. I mean, it's all in the same measure. But if I limit myself to a compact space, then I can cover it with an epsilon cover immediately. Now,
So now there is something important here, because I assume that there is a distribution measure, probability measure, on my space. I can always compactify it by throwing away only a delta part of this, delta measure away. So think about, for example, a Gaussian over the line. If I care only about probability 1 minus delta, for any delta, all I need to do is to cut out the tails which have measured delta. And then I have already a finite compact space. So the idea, actually, distributions actually allow me to compactify things which are not compact. Essentially, I throw away the things that have small measure. The only problem with this is that I don't have the distribution. I only have some sort of approximation to it, so I don't really know how to do it in practice. But so that's the idea. And how do you compactify things, or how do you cover? Of course, this is I'm not giving you an algorithm. This is, of course, we just want to generate at this point sample complexity bounds. And an algorithm require another course, how to do it, or at least a few more lectures. Okay, so now I want to actually give you, and somebody asked me, of course, correctly, did you actually show that there is uniform convergence for anything? No, the only thing we actually said is that there is uniform convergence for finite spaces. Finite spaces are, of course, just take the worst case there, and it's a bound on everything. So the supremum in this case is simply a maximum, and if you guarantee in the worst case, then it's a finite space, so everything is okay. The whole point is to go beyond finite spaces. So you already saw, at least, somebody see the eraser somewhere? No, the one on the table is not functioning. Okay. So now I want to introduce a very interesting measure. At this point, I think it's actually slightly, it's not as important as some people consider it, but it's still very nice. So it's called the whole section is called the VC dimension. Vapnik, Chervonenkis, something like this. Nenkis. Well, I'm not sure about spelling here. But, Vapnik-Chervonenkis dimension. It's a Russian name anyway, so. Two Russians, Vladimir Vapnik, and two of them are still here and still alive and still working. Vladimir Vapnik is even Jewish, and visited Israel many, many times. So I can even call him a friend of mine. So it's they did their work in the 70s and 60s, completely isolated for everything else. Published the results in Russian, and the whole thing was discovered to the West essentially only in the 80s. Okay, so what they did is essentially ask the question that we posed already. What is the condition for a class of function, H in this case, to have a uniform convergence of empirical means? And if you really look at this paper of Vapnik-Chervonenkis from 71, it's called On the Convergence of Empirical Means in a Class, or something like this, on the uniform convergence of empirical means, which is actually a question posed by mathematicians a long time ago. Those who learn some mathematics, it's usually related to the theorems of Glivenkin-Cantelli theorems and things like this, and uniform convergence in classes. But anyway. So the idea is that an hypothesis class H cannot be too complicated if it cannot label points in every possible way. So there's something which we want to call the growth function. So I use Amir's notation, which is somewhat confusing, but anyway. So of a sample. So I have a sample of size n. A sample of size n, again, was this set of points, x1, y1. Forget about the y's at this point. It's really not important for now. We have n points. So I'm given x's, just any points. I don't even say that they are sampled independently at this point. And I'm asking in how many possible ways my class can label them. So what is this? So essentially, it's the cardinality of a set for all hypotheses in age, age of x1 up to age of xn. So this is a vector of bits in this case. Okay, of plus minus 1s. Okay, so this is essentially the number of possible labels. It's called the gross function. It's not yet a gross function, but it's related to this. And so how many, what is the maximum number, what is the maximum cardinality of this set? Let's even put a number here. So this is the cardinality of this set. Yeah. So this is how many ways I can label endpoints. Okay. So what's the maximum? 2 to the n. Okay. Why 2 to the n? Let's make sure that you're here. Okay. So it's n bits. Okay. What's the maximum possible configuration of n bits? Is 2 to the n. Okay. Okay. So what is really interesting is the maximum over age of this number. So I call it pi age of n. So this is for a particular samples. So let's take this to be the maximum over all set Sn of this cardinality. I already wrote it as a number, so of this pi age of Sn. And this is what we call the gross function. Of age. So essentially, so this number is going to grow with n. At some point, it's going to grow like 2 to the n. But the question is it going to grow 2 to the n forever or not? So let's take an example, a very fundamental example. That's, I don't know, the intervals are maybe too easy, but okay, let's start with the interval. So you have the intervals between 0 and 1, and let's say that my classes of hypotheses are just intervals A, B inside 0, 1, okay? So age in this case is labeled by 2 numbers. So all the intervals, the indicator function of an interval A, B. I don't know what, when A and B are between 0 and 1. So in some sense, this is an hypothesis, okay, A1, B1. It's going to label this one with 1 and the other one is 0. This is another hypothesis, and so on. Okay, so let's see what is the gross function of this particular class, okay? So how many different points I can label? Okay, so 1 point, I can, of course, put it in. I find an interval that labels it 0, and I can find an interval that labels it 1. So obviously, 2 points. So I have 2 points. So how many possible labels can be there? 4. So can I find intervals which will label it with all the possible ways? So let's say, can I find interval which will put this 1 here and 0 here? Yes, of course I can. Can I find intervals which will put 0 here and 1 here? Of course I can. Can I find intervals that put both of them 1 or both of them 0? Of course I can. So 2 points in the interval. With the intervals, I can what we call shutter. Shutter in this case means I can label them in all the possible 2 to the n ways. So the question is essentially whether my hypothesis class shutters a sample of size n. Okay? So with 2 points, you all see this. I can find intervals that will put it in all the possible configurations. Okay? What about 3 points?
1, 0, 1.
Okay. So this should be clear to everyone. So with 3 points, let's say x1, x2, x3, I cannot label them, let's say 1, 0, 1, or 1 minus 1, 1. Why not? Because one interval if it covers both of the edges, it must include the third one. Okay, so 3 points cannot be shattered by intervals. Okay, and of course 4 cannot also be shattered, because if I shatter 4 points, I also shatter 3 points, and so on. So it seems to be that there is a maximum number of points that can be shattered by my class. Okay. If you think about rectangles, for example, in the plan, so what's the maximum number that can be shattered by a rectangle? So okay, so this is slightly more tricky, but you can see that any 4 points I can still shatter. Well, not any 4 points, by the way. If I put them on a line, I cannot. But I can find 4 points. So the maximum here, I can, over all samples, I can find, for example, I can put a rectangle here, or a rectangle here, or a rectangle here, or here. You can actually put all 3 in one, and so on. So there are rectangles that will shatter it in all possible configurations. Okay? What about 5 points? So 5 points, you can see immediately that you cannot shatter in general. There's no way you can shatter 5 points in general position, or even not in general position. In this case, you cannot shatter 5 points. So this looks like a nice quantity, this number, the maximum size of a sample that I can shatter. In some sense, so what's going to happen beyond the shattering point? How many possible configurations are going to be there? This is going to be an interesting question. We're going to answer it immediately. So I want to define this. So in some sense, if I have very rich, let's say I don't have one interval, I have a union of 2 intervals. So with union of 2 intervals, I can already shatter 3 points very easily, but I will not be able to shatter 5 points, or even 5 points I will not be able to shatter. With union of 2 rectangles, I can shatter more than 4 points, but not more than. So the maximum number, this is the maximum number for which this is 2 to the n, is going to tell me something about the complexity of the class. Okay, so I want to define something, and I hope I'm doing it right. So we call the VC dimension of H, VC for Vapnik and Chermanenkes, as what? So let's try to define it together. The maximum number of, so it's going to be the argmax over n for which pi h of n equals 2 to the n. So this is something somewhat tricky. It's the n that maximizes this, that obeys this. Okay, so all I said here, okay, pi n equals 2 to the n, this is what we call shattered sample. So since I took the maximum to mean that there exists a sample which I can shatter. If there exists a sample that I can shatter, then n is at least, the VC dimension is at least this number. So it's going to be, okay, no, of course not. But so this is a nice characterization. And so essentially we know that if it's finite, then beyond a certain point, this is not going to be to grow. So this growth function is not going to grow exponentially. Actually, it's not even clear that it doesn't grow exponentially. It's not going to be 2 to the n. Maybe you can say that it grows exponentially with another exponent smaller than 2 or something like this. But actually, no, it's not. It's not going. It's going to grow polynomially with n, and that's really the interesting part. So essentially, what is really, so this is a property of a set of functions h over some inputs, and it's a property which is very fundamental. I mean, something, can we shatter? So, for example, what can we say about it? Okay, so now I have really too little time to say much more. I'll say what I can. So there is a nice lemma, which actually was proved many times and have different names. It's called sometimes Sauer's lemma, sometimes it's called Sauer-Shelach. Saron-Shelach also proved it independently, and I think that Micha Perles also proved it independently, and many others proved it independently. So it has many names, but in most cases it's called the Sauer's lemma. Who else proved it? I mean,
No, I think Shach proved it twice.
yeah, independently, yeah. Yeah, okay. So it's actually not very hard to prove for people like Sharon Shelah. So he didn't even mention it as it was a lemma somewhere. But it's actually interesting. So essentially what it tells us that this growth function, the maximum over n over a set, is bound if it's, so this growth function, so this is the lemma which I will call Sauer, S-A-U-R-E-R. Something like this, but maybe I'm wrong. Sauer's lemma, but many others here. Oh, God. And it's actually saying that this growth function for a function h, if d is finite, if dvc is less than infinity, let's call it from now on d. So this pi of h of n is bounded by the sum I go from 0 to n of n over d. I think I'm right here. But d over n or n over d? Sorry, bounded by the time I go from from 0 to d. This is the whole point of n over d. N over I. N over I. Yeah. So what is n over I? It's the binomial coefficient. So these are all integers. This is the function which we sometimes denote by phi of d and n. This is just a notation. It's actually an interesting function. So I don't know how many of you, just to get, again, some intuition, I'm not going to prove it. I'm not going to prove it, although the proof is so nice that it's really tempting to prove it. It's, I get, but if you know the binomial coefficients, so this, what, if you really want to reconstruct them, I hope all of you know how to do it. So n over I is n factorial over I factorial times n minus I factorial. But of course, what is nice about them is that you can generate them using a recursive construction, which is known as the Pascal triangle. Okay, I'm sure you all know that. If not, this was worth coming to this class just if you don't know that. So the binomial coefficients are numbers that obey this recursion. How do I continue? So what we're going to be next line? 1, 4, 6, 4, 1. How many of you never saw this before? Okay, so these are the coefficients of the binomial. So essentially, if I look at this is d equals 0, this is d equals 1, this is d equals 2, and so on. And I goes from here from 0. So this is I0, I1, I2, and so on. So the assumption is that outside of this, everything is 0. Okay, just to make sense of this. So n over things which is larger than n is 0. Okay, so what is the nice property of this triangle? What do you know about it in terms of? So of course, every term here is the sum of the two above it. Okay, so there's a nice recursion relation, which means that n over k is what? Is the sum of n minus 1 over k minus 1 plus n minus 1 over k. So this is something you can easily or not easily prove yourself. So this is essentially the reason why this Pascal triangle works. And if you look at this bound, so this is Sauer's lemma, which, as I said, I'm not going to prove. Just going to give you some intuition about it. So the Sauer's lemma essentially is summing. So what is this? So you take D, and you fix D. D is known, and you sum all the terms in the triangle up to D, from 0 to D. I'm sorry. You take D and N, and you sum the first D terms in the nth row. This is what's written here. So let's write it like this. Yeah, I'm sorry. So this is n equals 0. This is n equal 1, n equal 2. Yeah, to agree with this. Okay? And now you take the nth. So n is the sample size in this case. You take the nth row of the triangle, and you sum D terms there. The first D terms, including 0. This is what this function is. Okay, so as long as D is less or equal n, what will it be? So I assume that everything outside is 0. Just to make sense of this sum. If D is larger than n, then you should tell me what do you mean by summing all of them. So below here, it's 0. Okay. So how much? So essentially, for any D which is small, which is larger than n, it's going to be the sum of the whole row. Okay. So the sum of the rows of the Laplace triangle are 2 to the n. Why is this? Okay. The easiest way to think about it is to think about it as 1 plus 1 to the n, and then you expand it. And you expand it in the binomial sum, and you get exactly the sum of the coefficients, or the powers are 1. Okay, so 1 plus 1 to the n. So as long as D is larger than n, or larger than or equal n, I'm going to sum a full line here. Okay. Now, once I start getting to n which is larger than D, I'm going to sum only part of the line. Okay. So let's say that D is 2, and yeah, okay, so it's a bit confusing, but so let's say that D is 2, and I'm summing this. So it's going to be 1, 2, 4, and then instead of 8, it's going to be 1 plus 3 plus 3. How much is it? 7. Less than 8. I'm missing 1. And then the next one is going to be 1 plus 4 plus 6 is 11, and so on and so forth. So the question is, how is this number, the sum of the D terms of the Laplace triangle, grows with n when D is larger than, when D is smaller than n? So if it's larger than n, I sum the full line. Here I get 2 to the n, but at some point it's getting below 2 to the n. When you see that eventually it will be very, very small because I'm summing out of this quadratic terms only a linear fixed number. Okay. So what do you think? By the way, so this is a nice way to think about it. At least that's the way I thought about it for many, many years. Somebody gave me this question when I was in high school, and I thought about it for a few days. So if you have lines in the plane, that are what we call in general position, which means no two of them are parallel, and no three intersect in the same point. Okay, so any random number of lines. So how many different so how many sets the plane is partitioned by such lines? So what do you think? So the answer is precisely this number. These are 3 lines. The dimension is 2. Okay? And if you count carefully, you'll see that there's not the number here is 1, 2, 3, 4, 5, 6, 7. It's precisely this. It's the third line because there are 3 lines, and the dimension is 2. So in this case, the dimension is D is equal to 2, and the number of lines is here. And if I'm right, with 4 lines, how many cells I have? Okay, so I give another line. How many more are generated? 11. It's 11. And check it. So essentially, it's easy to see why it's not that you already start to see the recursion behind it. So by adding another line, since I assume general position, it's going to cross all the other lines, which means that the line itself is going to be partitioned into n sections, and each one of them is going to partition one of the sets. So the number of sets that is going to be added is precisely the number of intervals that I cut on the line. So if you think about it for a moment, since a line is just an hyperplane in lower dimension, you get something which looks very much like the recursion of the Pascal triangle. So essentially, if I know how many different intervals are on the line, this is the lower dimension. It will give me how many sections are added here. And this is something which looks exactly like the recursion of the Laplace triangle. So those of you who actually followed me have the idea of the proof of Sar's lemma, but I'm not going to. So essentially, just writing a recursion like this for this function phi d of n, and see that it actually relates one dimension to the next dimension. So each time I add another line, I'm actually adding what I had before to the number of cuts in the lower dimension. Okay, so this is actually a solution. Surprisingly or not, this was a question in the Mathematics Olympiad in 1969 for kids, okay, to try to find this general number. This is what it is. Okay, so yeah. Okay, so this is the idea of, so what I want to show, so essentially what we have here is the following expression, that pi h of n is 2 to the n as long as n is less or equal to d, and it's bounded by something which I'm actually going to prove, that it's bounded by em over d to the d for n greater than d. So this is essentially, again, if you want, part of Sar's lemma, because this is simply a simple property of this function. Not m, n, sorry. It's written n in my notes. Okay, n. So the fundamental property of this function is that this is independent, this is exponential, and this is polynomial. It's polynomial in n. Okay. If you want to prove it as an exercise that this is actually bounding this, it's actually not very difficult. You multiply this by d over n, and then bound it by the binomial expression, where it's 1 minus d over n. So essentially, I can show you, it's very easy to see that d over n, the d over n, this sum is smaller than 1 plus d over n to the d, to the n. And by what is this? Well, this is bounded by e to the d. So this is essentially the whole trick. So this is, I'm not going to prove it, certainly not in the 1 minute that I have. It's not hard. Okay. So what is really interesting about it is that this gives us a polynomial bound. Remember, now the fundamental result that you need to understand is somehow that you get a relationship, a uniform convergence result in terms of the VC dimension. So essentially, the whole point is that I can now replace the cardinality of H with something which depends on the growth function. So the result that you want to prove, and of course I will not do it today, despite my all good dreams, is that you can